So give me another way of writing 2a. Don't focus on the cosine part of it yet. Give me what's 2a the same thing as saying?
2 times a.
Better than that yet.
A plus a.
A plus a. So if you can view cosine of, you were right, but I was looking for a plus a. If you think of cosine of 2a, meaning the cosine of double angle, 2 times some angle, as being the same thing as the cosine of a plus a, we can now use our cosine of a sum formula that we derived last week. So the cosine of a plus a, using the cosine of a plus b formula from last week, we would say this is the same thing as cosine a minus sine a, using last week's formula. And then this would simplify to cosine squared a minus sine squared a. And that's one of 3 flavors of cosine of double angle. This is one of the 3. Cosine of a double angle has 3 possible formulas. Here's one of them. Now, the one I have a box around, how can we modify that one a little bit more? Well, we can go 2 routes here. One way is to take the cosine squared a out and put in 1 minus sine squared a. So that would give you 1 minus sine squared a minus sine squared a, giving us 1 minus 2 sine squared a. So there's another possibility. You'll use the one that would apply to whatever problem that you're working on. And now instead of taking, let's go back up to this again. Instead of taking out cosine squared and putting in 1 minus sine squared, we'll take out sine squared and put in 1 minus cosine squared. So that would give us cosine squared a minus the quantity 1 minus cosine squared a. And when we simplify that, distribute the negative through, combine like terms, we end up with 2 cosine squared a plus 1. So in the cover of your book, when you're looking at the cosine of a double angle, there's why you have 3 of them. Questions there? We'll derive the formulas first, and then we'll go back to see how we can actually use them to solve certain application problems. Now we're going to do the same thing for the sine of a double angle. We'll rewrite this problem as the sine of a plus a. And then we'll now use the sine of the sum formula from last week. This is the same as sine a cosine a plus sine a cosine a, giving us 2 sine a cosine a, and that's it. There is only one identity for the sine of a double angle. Now, if I asked you guys how can we come up with the tangent of a double angle, if you were to answer that as saying, well, let's just take sine divided by cosine, you're exactly right. That would be a way of doing it. However, we got 3 options for cosine. So let's try a different method. Let's do the same thing as we've been doing with the other 2. Let's think of this as being the tangent of a plus a, and then using the tangent of a sum formula that we derived last week. The numerator is tangent a plus tangent a. Denominator is 1 minus tangent a times tangent a. And this becomes 2 tangent a over 1 minus tangent squared a. So there's your formula for the tangent of a double angle. Any questions? And like I said, no memorization needed on the exam. You'll have this available. I'm just showing you where they're coming from, where the derivations are coming, how you actually use these formulas, and again, there's the summary of all the ones we just derived. Let's take a look at how we could use some of these formulas. Example says, let's say that we know that the cosine of some angle is 3/5, and we know that the sine of this angle is negative. Find the sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. Let's try to determine which quadrant that we're in. What quadrant am I in if cosine is positive and sine is negative? Quadrant 4, good. Quadrant 4 has a positive cosine and a negative sine. So this is my angle theta. So again, we'll drop the perpendicular. Put that over there. Drop the perpendicular segment. We know that cosine is x over r. So r would be 5. My x distance would be 3 units. And 3, 4, 5 gives us the right triangle, so y would be -4. Questions with the triangle? Now let's go ahead and answer our 3 questions. What's the sine of 2 theta? Well, sine of 2 theta, according to the top of the page, is 2 sine theta cosine theta. So without drawing the picture and labeling the triangle, I would have had everything except the sine of the angle. I already know what the cosine of the angle is. That was given to me in the problem. So this will equal 2 times sine. Let's go to my picture. Sine is y over r, so that would be -4/5 times the cosine, which we were given in the problem, is 3/5. And we do the arithmetic, and we end up with a -24/25. Okay. Cosine of 2 theta, you have a choice, right? You have 3 options. 3 options for the cosine of a double angle. It does not matter which one you pick. You should get the same answer for all 3 of them. So I even forget which one I used. Cosine of 2 theta. With this problem, I just decided to use the 1 minus 2 sine squared theta formula. So this would be equivalent to 1 minus 2 times the sine of theta, which we used in the last problem, right? The sine was -4/5. So this would be 1 minus 2 times -4/5 squared. And we do the arithmetic, square the -4/5, get positive 16/25, multiply that by 2, take 1 minus that, and we get -7/25. So far, so good? Now, what about the tangent? Well, you have a formula for that, and if you decide to use the formula, you will still get the correct answer. But I believe, with this problem in particular, the faster way is you already have sine and cosine of this double angle, right? So tangent is still sine divided by cosine. So with part C, or to find the tangent of 2 theta, I believe the faster way is to simply take sine of 2 theta, divide that by cosine 2 theta, because you just found out what those two were. So -24/25 divided by -7/25 is the same as multiplying by the reciprocal, giving us positive 24/7. Those are the 3 values that they're looking for. Again, if you wanted to use the tangent of a double angle formula, you'd end up with the same answer. Just 2 ways of doing the same problem. Any questions or concerns out there? All All right, I'm going to have you guys try the next problem, see what you come up with. And the directions say find all 6 trig functions. Let's you and I just find sine, cosine, and tangent. We all understand that we would simply take the reciprocal of those to come up with the missing 3. But see if you can come up with sine, cosine, and tangent of theta. We'll need a right triangle over here in the left once I determine what quadrant that we're in, which we're told angle theta is between 90 and 180, putting us in quadrant 2. But we're also going to start off with the fact that the cosine of the double angle is 4/5. So cosine 2 theta is the same thing as 1 minus 2 sine squared theta. So I simply took out the cosine of 2 theta and put that in 4/5 in its place. So 4/5 is the same thing as 1 minus 2 sine squared theta. I'm going to solve this for theta, sine theta. So we can subtract 1 from both sides. Subtracting 5/5 from both sides gives us negative 1/5 equals negative 2 sine squared theta. Going to divide both sides by negative 2, which is the same as multiplying both sides by negative 1/2. So that's going to give us sine squared theta equals 1/10. And now we'll take the square root of both sides. And now is where we all know, when you take the square root of both sides, it should be plus or minus the square root of 1/10. However, what quadrant am I in? I'm in quadrant 2. Sine is positive, so I want the positive square root of 1/10, which when we rationalize the denominator, we end up with sine theta being, what's that, square root of 1 over the square root of 10. That's 1 over the square root of 10. So we end up with the square root of 10 over 10. There's 1 out of the 3 answers, right? There's the sine, we need cosine, we need tangent. Now I'm going to take this sine theta root 10 over 10 and use it to construct my right triangle. We know we're in quadrant 2. And we know that r is 10. And we know that y is the square root of 10. And now I need to find x. So x squared is equal to r squared minus y squared. So x squared would be the square root of, or x squared is equal to 90. X is the square root of 90, 3 root 10. And in a sense, you'd have to think, since you're going to the left, negative, be negative 3 root 10. So with that, we can now come up with cosine and with our tangent value. Cosine theta, which is x over r, that would be negative 3 root 10 over r, which is 10. No simplification needed there, right? And then tangent, which is y over x. Y is the square root of 10. X is negative 3 root 10. And the root 10s cancel each other out, and we're left with negative 1/3. So there's your sine, cosine, and tangent. You would just need to take the reciprocals of those and rationalize to get the other 3. Anybody need anything clarified there? I don't think you could have started this problem using the very first version of cosine double angle. If you tried to use cosine squared minus sine squared, right, you wouldn't get very far, because you only knew at that point what cosine theta was. You didn't have the sine, so you had too many variables to begin with. If you're happy, I'll move on. And if you're not happy, I guess I'll move on. Directions say simplify each expression, and we'll use our double angle identities for A and B. We recognize that cosine squared 7x minus sine squared 7x. The purpose of this is they're hoping that you recognize sine squared minus cosine squared minus sine squared as being one of your three double angle identities. So this would equal the cosine of 2 theta. Cosine squared alpha minus sine squared alpha is cosine 2 alpha. So all we have to do here is multiply 2 times 7x, and this is the same thing as the cosine of 14x, is what they're after there. Letter B, they want you to, and I would not have known to do this myself other than me looking at the description of the problem. But what they want to show you is you can be pretty crafty with some of these problems. Let's reword B as being the same thing as 1/2 times 2 times sine 15 cosine 15. What I just wrote, right, is still the same thing as the original problem, because 1/2 times 2 is 1, and you have the original problem, right? However, this part right here looks like what? Sine of a double angle. Sine of a double angle. So now we can rewrite this as 1/2 times the sine of what? 30. 2 times 15. The sine of 30 degrees is 1/2, and 1/2 times 1/2 is 1/4. I'm not saying if I hand you that problem you're going to see it the same way, but after we talk about the half angle identities, you could go back and do this problem using your half angle identities and get the same answer. Now for the next problem, sharpen your pencil. Our job is to take the expression sine 3x and come up with a equivalent expression that only uses sine x's, which means sine squared x's is okay. Sine cubed x's is okay. We just don't want to have it as the sine of some multiple of x. We want sine x. So let's take the sine of 3x, and to get started, think of it as the sine of 2x plus x. And now let's use the sine of our sum, sine of a sum identity. The sine of 2x plus x would be sine 2x cosine x plus sine x cosine 2x. And we'll simplify the sine of 2x. We'll use our new double angle identity here. Sine 2x is 2 sine x cosine x with the existing cosine x. And on the right hand side, we're going to take out this guy right here and replace it with the cosine squared minus sine squared version. So on the right hand side we have sine x times cosine squared x minus sine squared x. So to clean this up a little bit, on the left hand side we're going to multiply these two together to get a cosine squared. So we have 2 sine x cosine squared x. On the right hand side of the plus, we'll go ahead and use the distributive property. So we're going to have sine x times cosine squared x minus sine cubed x. And here's where I'm headed, folks. Here's where I'm headed. I got to see everything in terms of sine x in my problem. So what do you think I'm going to do next with where we're at?
Combine together.
Not yet. Nope, can't yet.
Or cosine for sines.
We're going to change cosine squareds to 1 minus sine squareds, right? So this guy comes out, 1 minus sine squared goes in. Also on the other side, we're going to have sine x times 1 minus sine squared x minus sine cubed x. A couple more steps and we're finished. We're going to have to do the multiplication again. So we're going to multiply, distribute the sine x through, 2 sine x through, here, here, and over here we'll distribute sine x through. So that will be 2 sine x minus 2 sine cubed x plus sine x minus sine cubed x minus sine cubed x. And now when I look at all those terms, I got everything in terms of sine x. Do I have any like terms? Here is negative 2 cubes, negative 3 cubes, negative 4 cubes. So altogether I have negative 4 sine cubed x's. And I got 2 sine x plus another sine x gives me positive 3 sine x. And there, folks, is an equivalent expression. I don't even think Ripley would believe that. So what we're saying there is we basically came up with an identity for the sine of a triple angle. There it is.
So that's the answer?
Yeah, that's an equivalent expression using nothing but sine x. Yep. Sine of 1x. See, notice the bottom? Sine 1x, sine 1x. All right, we're not going to derive all of these. We're going to pick one, maybe two, to derive. I'll show you where they're coming from, and then I'm going to show you why they're important. Maybe not as important in this class, but those of you sitting in this room that will eventually be taking calculus, these will come in handy probably towards the end of your calculus class. I'll show you why. What these are called is product of sum, and then down below we have sum the product. But notice what we're doing here. We're taking the product and translating it into a sum, or we're taking a product and translating it into a difference. And we'll just derive maybe one of these. Let's go ahead and derive the top one, this one right here. And the way we start off with is we start with the right hand side. So let's write out what's the cosine of a plus b and the cosine of a minus b. Cosine of a plus b. Now we're back to the cosine of a sum. That's cosine a, cosine b, minus sine a, sine b. And if we also take the cosine of a difference, which is cosine a, cosine b, plus sine a, sine b, take those two identities separately and add them together. Meaning we're going to add left hand side together, we're going to add right hand side together. On the left hand side, we get cosine a plus b plus cosine a minus b. Look what happens on the right hand side when we add those. Think of those 4 terms, right? You're going to add those 4 terms together. These would cancel each other out. One's negative, one's positive. So you're left with cosine A, cosine B, plus cosine A cosine B, which is 2 cosine A cosine B. And then you just multiply both sides by a half. So the way it's written in your textbook would be cosine A cosine B is equal to 1/2 of the left side. And you could come up with all of the other ones the same way. What would you do next? You have 3 more, right? Well, to get the next one, instead of adding, you subtract. To get the next one, instead of using cosines, you'll use sines and add. And then use sines and subtract to get all the other ones. How or why or when could something like this be important to you is you're going to learn in calculus 2 things. One's called differentiation and the other one's called integration. And when you differentiate or integrate, let's say you're asked to take the integral of x times the sine of x dx. Without getting into what this symbol means and what this is all about, just know this. It is much, much, much easier and this goes for both differentiation and integration. It is much easier to integrate a sum or a difference than it is a product. To integrate a product or differentiate a product, way, way, way more involved with integrating or differentiating a sum, a polynomial. You'll find out in calculus to integrate or differentiate a polynomial, it is okay to simply break it up into each of the terms and integrate or differentiate in each individual term. So as you can see, it will become important or imperative that you take trig products and somehow turn them into some type of product or a sum, allowing you to integrate or differentiate a lot easier, which is why they want to introduce those formulas to you now. So they come in handy later on. And again, it allows you to take some product and rewrite that product as a sum or a difference, allowing you to integrate or differentiate a lot faster. And then on the flip side of that, down below, you have the formulas that go in reverse. These formulas take the sums or the differences and translate them back into some kind of product. Those we won't be using all that often in this class. Okay? Let's take a look at a specific example. Says let's write this difference as a product of 2 functions. So I see that we have a difference of signs asking us to write it as a product of 2 functions. So this would be a difference to product, or in other words, sum the product. So it looks like we want this one right here. There's the one that we want. So the sine of A minus sine B is equal to 2 cosine something over 2 times sine of something over 2. And I fill in my somethings. I simply add A plus B together, and then I turn around and subtract A from B. What's A? A is 2 theta. B is 4 theta. A plus B, 2 theta plus 4 theta, 6 theta. A minus B would be 2 theta minus 4 theta, and that's a negative 2 theta. Now we'll simplify those a little bit. We have 2 cosine 6 theta over 2, ends up being 3 theta. And the sine of negative 2 theta over 2 would be the same as the sine of negative theta, but we have a negative angle identity that says sine of negative theta is the same thing as negative sine theta. So that negative will put out front, right? And we're left with sine theta. So there is the sine of 2 theta minus the sine of 4 theta as a product of 2 functions. Okay? We're going to do the same thing as the last section. We're going to come up with